I need to share my screen. Before we get started, I was surprised, pleasantly, I guess, surprised at the few number of emails that I got from people over the weekend. So before we get started on going back to live coding the two-way ANOVA, there's a place on the Moodle site now to turn in your one-way ANOVA report. So just deposit your materials there. It's going to be 2 files. It will allow you to deposit 2 files without any difficulty. To do the end of the day today. Do you guys have any questions about what you've been doing over the weekend in preparation for turning that in? I saw a number of you on Friday, and hopefully we got a lot of the questions answered then. What about the rest of you? Okay, well, good. I'm glad everything's going well for you. So, pull up the R script that you were working on last time. We had a lot of difficulties getting started, so hopefully those are behind us now. You should read in your data, make sure that your data are there and that they look correct. Once again, I've asked you to provide me two forms of the growth data. One form of the growth data is the growth data exactly the way they appeared in class, in the in-class example. And in that example, you'll recall, hopefully you'll recall, that there was a significant effect of fat type was significant, sex was not, and the interaction term, the sex by fat type interaction term, was not significant. And so what I've done is in the second set of data, I've just basically flipped the rancid male I've put in the fresh male category, and the fresh male I've put in the rancid male category. What that should do is that should turn it into a two-way ANOVA with a significant interaction term. We'll see how that works here in a little while. So we're going to actually go through scripting 2 different ANOVAs, one on the growth data, the original data, and then one on the manipulated data that I've moved around. So that's what we're doing today. So at the very least, you're going to need RMISC, ggplot, and CAR. Probably on Wednesday, we will be doing some other things with ANOVAs that will require some packages to be loaded that you haven't loaded yet. So expect between now and Wednesday an email from me, probably later on today, asking you to install some additional packages that we'll start using on Wednesday. So the first thing that we needed to do was we needed to set up the model. And you'll recall that Blaine had suggested, let me make my screen bigger. Blaine had suggested that we identify it or specify it kind of the way we had before. But remember, he suggested putting a plus sign in here. And when we ran the plus sign, what did we get in terms of output? Last time. I guess you could just run it and remind yourself. We got an ANOVA table, but the ANOVA table is lacking. What is it lacking? Yeah, it's lacking the interaction term. So you have to either tell it to do the interaction term by using the asterisk. And now you can see that the interaction term is there. Now notice in these two ANOVA tables, and I pointed this out last time, that the effective sex is the same, 3781. The effective fat is the same, 61204, because those are generated by looking at the row means and column means versus the grand mean. What is different about the two ANOVAs is the residual value. You see that the residual value in the model with the interaction term included is lower than the residual variation value in the original, and it's because some of the unexplained variation is now explained by the possible interaction between fat type and sex. And so when we think about sums of squares, sums of squares residual, or if you want to call it sums of squares within, or sums of squares error, these are all different ways in which different people refer to the same thing. All it is that there is, at the bottom of all of this, there's sum squares total. One way of thinking of the sum squares residual is sum squares residual is whatever is left over after accounting for systematic variation. So what I mean by a systematic variation is that there's some variation that is explainable by fat type. There is some variation that is explainable by sex. Any variation of the total amount of variation that is not explained by either of these things just ends up in the residual term. So whenever you're working on a project, the more you can actually assign variation to systematic forms of variation, the lower your residual term gets. The lower your residual term gets, the easier it is to see differences, because when you test differences, you're always testing the F statistic, which is the mean squared of whatever treatment you are looking at, divided by the mean square residual. The lower this gets, the bigger this gets, and the more likely you are to see a difference when a difference occurs. So by not including the interaction term, we just take that systematic variation that is due to the interaction of sex and fat type, and we dump it into residual. That makes residual bigger, that makes F smaller, makes it harder to see differences. So make sure that your models that you use are always fully specified, because then you account for all of the systematic forms of variation, and that reduces your residual value. Now we could also have specified this model by saying, well, what happened there? I was off a little ways. If you do this, that should give you the same result. But once again, why do all of this in front of that when you can just identify the interaction? When R sees that there's an interaction term, it assumes that there's a main effect of one of those treatments, a main effect of the other of those treatments, and it will calculate those. So all you really need to do to get it to give you the output you're looking for is to specify the interaction. So that gives us the model, and we see what the ANOVA table is. We actually didn't need to run the model in order to get the model in the system, but we want to specify that model because by being able to type in model 1, what are the things that we can do? What's the first thing that you do at the beginning of an analysis? Yeah, why are we going to be getting residuals? Okay, so we want to test our assumptions. So what's the syntax for getting residuals? Okay, since we've already given our model a name, we can just type residuals, and then in parentheses we can put model 1, And what it should do is it should run model 1, and then it should give us the result. So let's see if that works. So it looks like it ran without error. We should be able to get the residuals, and there should be 12 residual values, and those residual values should have a mixture of positives and negatives. It looks like that is correct. Now, one of the problems that we have here is we only have 12 observations total, and as a result, we don't have a lot of statistical power. And so, how do we test normality? Thank you. I'm actually asking questions because I want you guys to answer me. You notice that what I am not doing, Shapiro test, and what are we going to test it on? Whatever you called your residual. And we see that we have good conformity to normality. Now, you have a very non-significant Shapiro-Wilk test, which means that your data do not differ from normality. But that could be because you have really normally looking data, or it could be that you just don't have much statistical power to test this on. So how do we get a look at what these data look like? Haley. Yes, histogram. What's the code for that? Hist. There you go. Hist and what? Yeah, whatever you're calling residuals. Why did I call on you? No, I called on you because you asked me about how to make history up over the weekend. What? What?
I said I would be.
Oh, okay. All right. No. It wasn't that reason. So this is a histogram of the residuals. And quite frankly, the residuals don't look non-normal, but they don't necessarily look normal. There's a big gap in the distribution, and it's just really difficult to tell if this is normal or not. So this gets back to the thing that I sent you over the weekend. I meant to mention this on Friday because I had talked to students about this on Thursday. When you test normality, sample size matters, just like sample size matters anywhere. So here we have a sample size for Shapiro-Wilk's test of 12 observations. Even if you've had really non-normal data, you might test for a difference between normality versus not normality, and you might find that you don't reject the hypothesis that the data are normal. And it's not because they're normal, it's because you just don't have any statistical power to make that test. In your data set that you're working on with the geckos, you have 182 observations. With 182 observations, you have a tremendous amount of power to see even small niggling differences, deviations from normality. And so one of the things that you always have to consider as you're doing things like testing assumptions is you have to consider how much statistical power do I have to basically distinguish between whether a distribution is normal or not normal in terms of its distributional shape. And with a sample size of 12, you have hardly any power, and with a sample size of 182, you have way more power than you actually need. And so this is where judgment comes in. A lot of times people think, and I used to think this myself when I was younger. I was actually taught by one of my statistics professor that for any given data set, there's one most appropriate way of analyzing it. I believed that actually when I was younger, but I'm a little looser about that nowadays than I was when I was younger. I can see that there are various ways of looking at a data set. There are certainly some ways that are totally 100% inappropriate, but on any given data set, I can usually think of a couple of ways in which I might want to ask questions of that data set. Same thing about statistical testing. Just because you see a particular p-value, and in the case of testing normality with the gecko data, you saw a p-value. This is technically lower than 0.05. So you would conclude those data do not conform to a normal distribution. But one of the questions that you have to ask yourself is, are the data really not normal, or do you just have a tremendous amount of power to see even teensy-weensy deviations from normal? Now, when you go and graph the data as a whole, the data really don't look that non-normal. There's a little bit of outliers at the high end, and typically the way we get rid of outliers, the way we get rid of what we call positive skew, data that look like this, and the gecko data don't look anywhere nearly this skewed. Typically the way we do that is we can either take the square root of the original data, or we take the logarithm of the original data. In both these cases, what square roots and logarithms both do is they leave small values pretty much alone. The square root of 1 is 1. The square root of 4 is 2. The square root of 16 is 4. So small numbers don't really change that much. The square root of 100 is 10. Takes that 100 that's way out there and brings it way in close to the other data points. So what both of these things tend to do is it tends to move these values out here, moves them closer in here, and as a result of that, compresses this whole thing and makes it normal. What you find with the gecko data is you try those two things, actually things get worse rather than getting better. And so the two typical transformations that you use to deal with positive skew don't serve you in this case for whatever reason. But because you have a couple of things going for you, the data, if they are non-normal, they're not very far out of non-normal. Also, the normality assumption is more about the distribution of sample means than it is about the original data. So you can invoke the central limit theorem because for all of your samples, you have more than 30 observations, 30 or more observations. I think it was 30, 40, 52, and 60. So you can rely on the central limit theorem that if you draw means out of those populations, you're going to have a distribution of sample means that will be normally distributed even if the original data or not. That's why we spent so much time at the beginning of class talking about the central limit theorem and sampling theory. Not only that, most parametric statistical tests are robust to deviations from normality. So I don't usually get all that worked up about normality and deviations from normality, especially when I have 182 observations in the test. Homogeneity variances, though, is the more serious issue. And recall from the beginning of class, after we started talking about parameters, I talked to you about the issue of variances being different makes it difficult to make decisions in statistics, but they only really affect your decision making when you have one population that has a really wide variance and another population has a really narrow variance, but this other population has a narrow variance and is found in a way that if you look at their population means, you find that this mean definitely lies outside of this population, but this mean definitely falls within this population. That way, if you're comparing population A to population B, and you ask, could the mean of B have come population A? The answer is a resounding yes. Yeah, sure. That mean could have come from this population. But when you ask the opposite question, could the mean of A have come from population B? The answer is a resounding no. That mean could not have come from that population. So in this case, what decision do you go with? That the two things came from the same population, or that the two means came from different populations? It's ambiguous. But what you have in the case with the geckos, you don't have a situation like that. You have two populations that are pretty normal, but they're at the high side. You have another population that is not terribly normally looking, that's down a little from that one. And you have another population that's really pretty non-normal, that's further away from both of these and this one in terms of its overall distribution. So even though you have a lack of homogeneity of variances, what you don't have is you don't have these distributions overlapping a lot. The only distributions that you have overlapping a lot are actually these two, which are the summer collections. I've drawn this actually a little incorrectly. The winter Galveston, if this is summer Galveston, summer Oklahoma City, winter Galveston overlaps just a little bit with summer Galveston, and winter Oklahoma City doesn't really overlap with any of them. So nowhere in these data do you see a situation that looks like this. So once again, you're faced with a homogeneity of variances issue. The transformations that we attempt don't fix the problem. When you go and look at the distributions of the data, you look at them and you're like, well, that's not as big of a problem as it could be, because when I look at the actual distributions of the data, they themselves are not overlapping, except in the one case where the statistical test found no differences anyway. So statistical judgment is an important thing to develop. You guys are probably not at the point where you can do that, which is why I wrote you a really long document to explain my reasoning behind why I want you to just go ahead and deal with the raw data, because there's really nothing you can do about the fact that they're not normal and they have variances that differ from one another. But in the end, it doesn't probably have any influence on your ability to make a statistically valid decision at the end of the day. And the statistically valid decision or conclusion is summer temperatures are the same everywhere. Winter temperatures are different from summer temperatures, and the winter temperatures are also different from one another. And that would hold up regardless of whether you violated these assumptions or not. So you might look at this result and say, woo, we're good. But you have no freaking idea whether that stuff is normal or not. Why not? Because you have a sample size of 12. And I can throw you up some uniform data, and chances are, if you test it at a sample size of 12, it's also going to return a non-significant Shapiro-Wilk test. Simply because you don't observe a significant Shapiro-Wilk test doesn't mean that you have normally distributed data. It could just be that you have crap sample size. Okay? This is why his should become your friend. Do not be afraid of looking at the raw data graphed in something like a histogram. That can be very informative to you. In some cases, it makes you breathe a huge sigh of relief, like in the gecko data. In other cases, you're like, oh crap. That looks wonky. And so get used to running histograms on your data here at the beginning. What's another way in addition to looking at a histogram that we can look at our data? Yep, QQ norm. And actually, when you look at it this way, it doesn't look too bad, although a full quarter of your data set is kind of off the expected line. So remember what a QQ plot does is it plots what you would expect your data to be, which is the line, and what your data actually are in terms of cumulative percentiles as you go through it. And so here you have 1, 2, 3 points that are pretty far away from the expected. But in this case, those 3 points, that's a quarter of your data set. So once again, simply because you have observed a Shapiro-Wilk test that is not significant doesn't mean that your data set doesn't potentially have problems. It's just that you can't see it because a quarter of your data set is out of whack. In the Gecko data set, I think it was 6 or 7 points that were above the line in the high temperature range. But that's 6 or 7 data points out of 182. Once again, is that something that should be concerning to you? Well, that's where judgment comes in. Now, we don't have any choice about this data set because this is a data set that somebody brought us. And so this is what you have. Nobody's going to be testing more rats in this case. So this is what you have to go with. You can always fall back on the p-value and say, well, it's not different from normal. And remember that simply saying that two things are not different is not the same thing as saying that they're the same. Because you're saying that I can't find any evidence to say that they're not different from normal is not the same as saying it's normal. Those are actually different statements. One of the reasons that we test data the way we test them, we're testing for differences, we're not testing for sameness. And it's because the bar is much higher to say two things are equal than to say two things are not different. And that's what we're really, you basically have to have the entire population measured to say that two things are equal. You don't need the entire population to say that you have enough evidence to say that two things are not equal. And so simply because we find that there's no evidence to say that this distribution is different from normal, it's not the same thing as saying, yep, it's normal. Because chances are, it's probably not in this case. But we're going to press on. What's the next thing we need to do? What's that? Yeah, Levine's test. So keep in mind that the first one doesn't work anymore, and it gives you a little error. These functions were deprecated in 2009 and are now defunct, so don't use it. Now, don't ask me why it gives you that as your first choice. Seems like if it's defunct and you shouldn't be using it, they just shouldn't give you that as an option. If you're using tab complete, use the second one, and then model 1. And once again, this shows you that you have no significant differences in the variances. But once again, this could be because the variances are very similar, or it could be because you don't have very much statistical power to test for differences in variances. How can we get a feel for what our variances are actually like? Oh yeah, we should do that also. Center equals mean. It's going to give you virtually the same result. I always forget to do that. It helps if one can type. yeah, it put a dent in the probability value, but not much of one. But what that probably also means is that the reason that center equals median and center equals mean is different is probably because you have some skew in your data somewhere. Keep in mind that the median is the point where 50% of your data lie above that value and 50% of your data lie below that value. In a normally distributed distribution, the median, the mean, and the mode are all at the same place. In a skewed distribution, the median is somewhere over here. The mean gets pulled in the direction of the skew because these positive values are pulling the mean up because they're extreme positive values. But if you cut this distribution in half of the distribution is over here, half of the distribution is over here, and then of course this is where the mode is. So whenever you see your Levene's test changing a lot when you test versus the median versus when you're testing versus the mean, if those things change a lot, chances are you have some skew in your data because of the effect that skew has on where the mean lies. And that's actually one of the reasons that the median test is the default in R, is because the mean tends to get pulled away by skew. And so the people who programmed this particular function in R made the median the test that it runs as a default because the median is less prone to variation due to outliers. Now, because we are always testing if means are different from one another, I tend to want to know, is the variance different from the mean, because that's the thing that we're actually testing. So good point, Chance. Thanks for that. I always forget that until like going back through my code and I'm like, oh, damn, center equals median. So once again, so how can we get a look at these? So it's not significant, but we also know that we have low sample sizes. So how can we take a quick gander at the data? The ANOVA table doesn't tell you what the means and the variances are. What gives you a breakdown of what are your means, what are your variances, what are your standard deviations, your confidence intervals, all that? Yep, summary SE. What's the syntax? So the first thing we need, remember that the little yellow box turns up. The first thing that you need is the data, which in this case, for my data set, I've now been so far away from it, I don't remember. I always use that. What's the next thing that we need? Measure var. What is the measured variable? The measured variable in this case is, in my version, is growth. And remember that you have to put this in parentheses or quotes. If you don't, it will groan at you here in a minute, and then you will remember. What's the next thing that you need? Group vars. And now it makes sense to you. Why has it always been group vars? Well, because in this case, you actually have two groups. So it's group vars plural. You can concatenate this and put, in my case, it's fat is one of them and sex is the other. And that should Do it. Get that to produce that for you. So when you get the output, well, put your green stickies up when you get the output, so I know that everybody got it to work. Green or blue. Sam, what's up? Oh, you have some NAs in your data. Let me see your data file. Just show me the whole thing. That. Just type in that. Yeah, that's telling you that. Yeah, don't worry about it. That's one of those. That's one of those error codes that when you read it, it's like, oh, I have NAs. I have lines in my data file that don't have any data in them. It's just giving you a warning that it gives you a warning that it saw that. So basically, you're trying to calculate a confidence interval, and you had some NAs. And so that's going down as you have one observation that is NA, but you still have all of your other treatments. Yep. So when you look at this, you see that we have fresh male, rancid female, rancid male. Sample size is 3, which is what you should expect. Here are the averages. Fresh generally have higher averages than rancid. But when you look at the standard deviations, what do you notice about the standard deviations? Two of them are really high and two of them are pretty low. As a result of that, the standard errors, you have 2 high standard errors, 2 low standard errors. And for the confidence intervals, you have 2 confidence intervals that are really wide and 2 that are really narrow. But you've had a non-significant Levene's test telling you that you don't have any problem with differences in variances. That's not because you don't have problems with variances. It's because you don't have the statistical power to detect those differences, even though those differences are pretty big. But you have sample size of 3 for each of your different treatment combinations. So in the same way that you can't always you can't always just look at the p-value and take the p-value as the gospel. Because the p-value would have told you, what was the p-value for the Levene's test, 0.246 or something like that? That's what that p-value means. That p-value means that the variances are not statistically different. You don't have the statistical power to determine that any differences that are there are actually worth paying attention to. But it's not because the variances are similar to one another. It's just that you don't have much power to determine that. Students, especially young students, oftentimes get caught up in just paying attention to p-value. What's the p-value? What's the p-value? What's the p-value? You should never look at a p-value without understanding the data that went into that p-value clearly. Just because I got this doesn't mean that I might not have some issues. And we'll see what that looks like here in a minute. Okay, so from the standpoint of statistical correctness, though, we can proceed because we have a non-significant test for normality and we have a non-significant Levene's test. So what are we going to do next, Sam? Yeah, let's go ahead and generate the ANOVA table. We've already created the model, so all we need to do is get the summary of it. And we've already revisited this. We calculated it ourselves by hand. But it's basically telling you that there's no effect of sex. There is a significant effect of fat. there is a sex by fat interaction that is not significant, and then this is the residual variation that is left over. So it's telling us that the two fat types are different. It doesn't tell us which direction they're different, although when we look at the summary SE file output, we can see that generally fresh fat produces higher rates of growth than rancid fat. Not surprising. Who wants to eat rancid fat? It's disgusting. So we have that answer. What else might we want to do? We found a significant effect. Yeah. Yeah, you might want to do a Tukey's test. Is that what you're going to say? Yeah, just shout it out.
No.
Oh, what were you going to say?
I'm going to say, like, since we can,
Yeah, so in this case, the Tukey is going to tell us the same thing. And one of the nice things about the Tukey is it will generally tell you the direction of the difference. So let's go ahead and do that. So when you get the results from the Tukey's analysis, in the end, it's going to give you the interaction, and that actually does all of the pairwise combinations. And what I want you to pay attention to in this Tukey's table is that it's always expressed as one thing minus another thing. So if we want to get a handle on what the effect of fresh versus rancid is, we could look at this one, but we could also just look at the main effect of fat, this one right here. This is what's driving the whole thing. And since this is rancid minus fresh, the difference is a negative, which basically means that fresh is bigger than rancid, because when you take a small rancid value, subtract a large fresh value, it gives you a negative value. This is the difference. And so back to this issue of, well, which direction is the difference? If you run a Tukey's on it, it will tell you which direction the difference is, because this difference will have an associated sign attached to it. It will either be positive or negative. If this is positive, then the first thing is bigger than the second thing. If it's negative, the second thing is bigger than the first thing. And so, once again, paying attention to the details of the Tukey's output will tell you what's bigger than what by the signs that are attached to those differences. So, in all the cases where these things are significant down here, it's always a comparison between rancid and fresh. Rancid, fresh, rancid, fresh, rancid, fresh. Rancid, rancid always gives you a non-significant result, and fresh, fresh always gives you a non-significant result. So the main effect is due to fat type. So now we know what the nature of the differences are. What might we want to do? Yeah, create a meaningful graphic. All right, let's get started on that. So, what do we begin with? Okay, what's the first thing that we get? You look at the yellow box, and the first thing we need is the data file. So in this case, what data file are we going to want to pay attention to? What data frame? Yeah, for me it's CI plot, whatever, wherever you stored your summary data. Because what you're wanting to do is you're wanting to graph means, confidence intervals, etc. So this was one of the things that was tripping a couple of you up in creating graphics of the Gecko data. You were trying to get it to give you a confidence interval graph, and you were using the raw data, and then it gave you a error that basically said could not find object not found CI. And it's like, why can it not find the confidence interval? Well, because you asked it to reference the original data set, not the summary data set. So after we tell it what data set that we want it to look at, what do we want to assign? Aesthetics. And in the aesthetics, what do we define? We define the X. In this case, X is now you've never graphed data with two different treatments. So this is a situation where you have to think a little bit about how you want to graph things. I tend to put on the x-axis the treatment that is the most significant. So in this case, I would put fat type on the x-axis. What is the y variable that we're graphing? We're doing growth. Yep. But now we don't have sex anywhere. So how do we get sex into this? How would you find out if I wasn't here to tell you? Okay, so you could Google it. Better yet, are you guys aware of the R graph gallery? Anybody familiar with the R graph gallery? Oh my God. You can, okay, maybe you can't, but I certainly can. You can just blow hours going through the R graphics gallery. So the cool thing about this is that it breaks things up into the kind of graph that you want to make. So let's see, what kind of graphic are we trying to make? We're trying to make a oh, well, crud, it doesn't have the chart type that I'm looking for. I was about to sell this to you, and now it's totally let me down. Well, let me just show you what this is about. This is a cool place where you can basically go and say, all right, well, I want to make a bar plot. So you can click on that, and what it does is it gives you a bunch of different kinds of bar plots, and it gives you the basic R functions, but then it also gives you ggplot ways of going about doing it. So what you can basically do is if you want to click on in ggplot, you want a bar plot with error bars, you can click on that, and why is it not working? Well, it came up a minute ago. Well, I was incorrect. It doesn't give you any scripting. That's irritating. Oh, there it is. Okay. Yeah, it's changed since last time I looked at it. Yeah. So if you click on the code thing, I was scrolling around looking for blocks of code. Um, so this is basically an R Markdown document for HTML. And if you click that, it will basically give you the code for how to create this particular type of chart. So unfortunately, it doesn't have what we're doing anywhere in here. What's that? Where are you seeing that at? Right there. Oh yeah. So yeah, so I'm just not seeing the word group anywhere. Oh, okay. Okay, there is a group. Yeah. Yep. Okay. Yep. Yeah. So let's just try that. So type in group equals, in this case, sex. Now, when you run that, it's going to run just fine. It's not going to give you anything because, of course, you haven't asked it to do anything yet, have you? So what do we have to do? We have to tell it to plot something, right? What do we have to tell it to plot? You want a bar? You want a plot? A point? What do you want? What kind of plot are you trying to make? Hmm? Oh, so you might want to do error bars. Okay, so let's do error bar. You're going to need error bars. But what goes in here for plotting an error bar? Well, we need to tell it the limits, right? Ylim, it's not ylim, ymin is equal to what? We're setting the minimum and the maximum of the error bar. The error bar is made up of the confidence interval, the mean plus the confidence interval, and the mean minus the confidence interval, right? So if we go up here and we rerun CI plot, what column is mean in? Well, the mean is in the growth column, and the confidence interval is in the column CI. So down here in our plot, we can identify the min as growth minus the confidence interval. So Y max would be what? Growth plus the confidence interval. So now we've done that. So if we run these two lines of code, it should give you something, but it's not giving me anything because I actually assigned it a name. Probably shouldn't assign it a name until the end. So it has given us a a graph that just looks like crap, but it has different means with standard error bars within fresh and rancid. It's got this terrible gray background. It's got really long whiskers, but it has all of the information. It's dividing things up by fresh and rancid, but it's also dividing things up, presumably, um, by sex. So we can get a better feel for that if we add something additional to this plot, which is geom point. And when we run that, what we should see is we should see 4 means. What that 4 means tells us is that you were right in that a grouping variable is what you need in the aesthetics, because it's grouping by sex. Now you can't tell which of those is which sex right now because we haven't assigned anything to that. But one of the ways that we can do this is we can do this with color. By adding a color statement in our aesthetics, we now have males and females appearing as different colors. And for whatever stupid reason, female is pink and male is blue. But it's not a great looking graph yet, is it? Okay, what would make it better? Okay, make the width of the error bar smaller. Well, that's certainly somewhat nicer. What else could we do? Oh, okay, so we could go theme classic. You're now a fan of theme classic. That gets rid of that gray background. So you have a much cleaner sort of thing. But what's the most irritating part of this graph as it currently stands? Or at least irritating to me. It's actually driving nails through my skull at the moment. Yeah, all your data are sitting on top of one another. So go outside of your graphing block. Do a thing called position dodge. And when you run that, it's going to give you nothing. You've just, actually, I wanted to do an assignment operator, not an equal sign. Assignment operator. And then, within your error bar, put position equals PD. And what you will see is it has basically moved your error bars apart. Now, unfortunately, we did that with error bars, and we didn't do it with the points themselves. So in order to get our error bars to go with our points, we also have to position dodge our points as well. And when we do that, we now have our means, we have our standard errors, and they're no longer overlapping with one another. Yeah.
It's not working. Position dodge.
Position dot dodge. Dot dodge, not underscore.
Oh, you have underscore.
Do I have an underscore? Oh, I do have an underscore. Oh, okay.
Should I try dot?
No, don't try dot. And you ran that?
Yeah, that's what I got.
Okay, but you didn't put position equals PD in your.
I didn't run this. I just ran this. And
Oh yeah.
this is what I
You got an
here.
error down there. Da, 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 da. But you got this to run just
I
fine.
haven't ran that yet, though.
Oh, you haven't run that yet? What have you been doing with your time?
Just typing it in, waiting for it to be done.
No, this is how you build up a plot. You start small and add. Yeah, but still. Still, you're getting an error. What did you just do?
I ran it. I don't know why that happened. I don't know what happened.
Okay, so that's working. That's weird. You're like in some debugger or something. All right, so that's still. I don't know how you got into this. I've never been in that before. Um, so it looks like this is running fine now. This line, you're not getting any error. So now put position equals PD. In the specifications for geom error bar and geom. Point.
What?
And in geom point.
Oh, and
Yeah, if you only do it one place, it's going to separate your error bars from your. I'll try that. Yeah, there we go. Yeah. Everybody else get something that looks like this? Okay. So in this way, we have a situation where we can see that fresh is generally higher than rancid, but males tend to grow slightly higher than females, although that difference is not significant. In interpreting a interaction term, what did I say one of the best ways to look at an interaction term is when you look at it in a graph? If these lines are parallel, what does that mean? Versus this, or this, or this. What does this mean? Talked about this last class period. You guys recall, you just don't recall. Okay, so the first one is no significant interaction. Fresh fat and rancid fat are affecting males and females the same way. Males and females both benefit from fresh fat, are both negatively affected by rancid fat, and they're both affected in similar ways. If this was the situation where this was fresh and this was rancid, females, well, let's say that this is the female line, and this is the male line. Males benefit from fresh fat, whereas females are negatively affected by fresh fat. Females are positively affected by rancid fat, and males are negatively affected by rancid fat. An interaction is when one treatment has different effects in the different levels of the other treatment. And so fresh and rancid fat are affecting males and females differently. Here, fresh and rancid fat are affecting males and females exactly the same way. This is an interaction term. This is a significant interaction term. This is a significant interaction term. This is a non-significant interaction term. So what would help our receiver of these data in wrapping their head around whether or not that interaction is significant? Maybe adding some lines. Oh, but guess what I didn't do? What did I not do? I didn't dodge the position. Boom, chicka boom. So now you have the beginning of a plot. A lot of other things you can do to pretty things up about it, but you have a functional plot. And because those lines are basically moving more or less in parallel, it signifies to the receiver of the graph, oh, this is why that interaction term is not significant. It's because these things are moving in parallel with one another. Homework for Wednesday. Do the same analysis on your own. I would start scripting from scratch. Analyze the second column of growth, which should have a significant interaction term in it. Questions?
What are the two things for a project? Is it the markdown file?
Markdown file and the summary, the report. Yep, those are the only two things. Yep. All right, things that went well, things that didn't go well on your stickies. And come in on Wednesday having worked through the other set of data with the significant interaction term.